if we have a rigid object with shape, we can start with the net torque equals I times alpha. Now, the net torque equals I times alpha. This is actually the external torques. So this is all the torques acting externally to the object rather than any internal torques, which wouldn't actually cause it to have angular acceleration. Only external torques to the object are going to cause an angular acceleration. Well, we could take the integral of both sides. We get the integral of the net external torque is equal to, with respect to time, is equal to the integral of the moment of inertia times the angular acceleration with respect to time. All right, on the left-hand side, we know that the net external torques is equal to the derivative of the angular momentum as a function of time. So the integral of dl dt with respect to time. That's on the left-hand side. Well, we have the dt's. The dt's can cancel here. So they have the integral of dl. What do you think the integral of dl is, Meg? The integral of nothing with respect to L.
Oh, L.
It's just L. Okay. So on the left-hand side, we have the angular momentum. Now remember, this is a rigid object. The rigid object with shape means its shape is not changing. So what can we do with the letter I, the moment of inertia underneath this integral? Second?
It's constant.
So what can we do with it? We can take it out. We know because it's a rigid object, it's not changing shape, so this moment of inertia we can take out. What is the integral of angular acceleration with respect to time? Zach?
Angular velocity.
Angular velocity. In other words, the angular momentum of a rigid object with shape is I, the moment of inertia, times the angular velocity. So again, notice we have two different equations, just like we did for center of mass and moment of inertia. We have an equation for the angular momentum of particles and the angular momentum of rigid objects with shape. For an example, let's just figure out the angular momentum of a solid sphere. Let's say that the radius of the sphere is 0.25 meters. The mass of the sphere is 1.0 kilograms. And the tangential velocity of an outside edge on the rim of the solid sphere is 2.0 meters per second. So we're going to figure out the magnitude of the angular momentum. We need the moment of inertia of a solid sphere about its center of mass, which we can look up. It is 2/5 mr squared. So the angular momentum is going to be equal to I times omega. We have the moment of inertia. It's 2/5 mr squared, but we're stuck with this angular velocity.
Velocity equals r times omega.
We know that the linear velocity equals r times omega. So we can, let's do it this way. So the angular velocity then equals the tangential velocity divided by the radius. So this is equal to 2/5 mr squared times the tangential velocity divided by the radius. One of our radii cancel out, and we get 2/5 mr times the tangential velocity. We have all of these 2/5 multiplied by the mass, which is 1, radius, which is 0.25, and the tangential velocity, which is 2. Two times 2 is 4, times 0.25 is 1. Dimensions on this, Stazel.
Kilograms times meters squared over seconds.
we have moment of inertia multiplied by angular velocity. Dimensions on moment of inertia, Stasel? Yeah, I'm trying to figure out how you got this, right? So the angular velocity is going to be in terms of what are the dimensions on dimensions on moment of inertia. Potterella. Taking this down here, we're just trying to figure out the dimensions. So I'm doing moment of inertia.
Yeah. So it's kilograms times meters squared times radians per second. And then radians, it isn't anything, so it means right.
I agree, he's right, I just wanted to get there.
Oh.
Radians are a placeholder, as you recall. So we don't need those in there, and we just end up with kilograms times meters squared divided by second. Good.